Assalamualaikum and good day to all. So we are going to discuss topic 8, which is magnetic field. Let's start. Okay, so here we are going to discuss about the definitions of the magnetic field and how to use the right hand rule to find the magnetic field or force or current. Okay, and then we are going to find the relationship between the magnetic force and also the current carrying wire, and also we are going to change the current into charge. So we are going to find the effect of velocity to the magnetic force and how to find the direction, whether it's going to be force or velocity or magnetic field. And the last one, we are going to discuss about one closed loop, whether it's moving clockwise or anti-clockwise, and this one going to relate with the torque. Okay, so let's start. Okay, the things that you need to understand about the magnetic field. The magnetic field is basically known for century. Okay, so it's mostly used in the magnetic needle. Okay, and the magnetic field is basically closely related with the magnet bar. Okay, when we talk about the magnet bar, this magnet bar is made of ferromagnetic material. Okay, ferromagnetic material. Okay, before this magnet bar have a pole of north and south, basically what happened here inside the magnet bar, the directions of the magnetic going to be in random directions, so it's going to be like this. Okay, but if you expose this magnet bar into a magnetic field, what happened is this line of magnetic field are going to be aligned, and what happened is going to show the directions of magnetic field, which is from north to south. Okay, and it's always be in a closed loop. Okay, so like I mentioned before, the magnet bar, it consists of two poles, which is north pole and south pole. So it seems like the one we discussed before, which is charge, which is come in positive and negative. But the difference is going to be, when it comes to the charge, you are going to have like one isolate charge, like one positive or one negative. Okay, but when it comes to the magnet, it's always come in pair, which is north and south. So example, if you cut this thing, what happened is you are not going to get one bar only with north and one bar only with south. You are going to get a new bar which is consists of north and south, and another one is going to consist of north and south. Okay, so the same thing about the concept of the charge before is like north. Okay, same pole. Okay, same pole, you are going to have a repulsive effect. Unlike pole, you are going to have attractive effect. Okay, so the things that you need to understand here is Earth itself is a one large permanent magnet. So we are going to discuss this one after this. Okay, so the things that you need to understand here is it's not possible for you to find one magnet bar that we can call it as a monopole. Okay, monopole means that you only have one bar with only south, or you only have one bar with north. Okay, it's very impossible for that. Okay, because it's always come in pair, north and south pole. Okay, when we talk about magnet, definitely we are going to relate with the magnetic field. Okay, so when we relate with the magnetic field, it means that this concept is almost the same like the electric field, where the magnetic field always tangential to the line at any point, and the magnetic strength are going to affect the magnetic field line that comes from the magnet bar. Okay, so if example you have like 2 Tesla, it means that these 2 Tesla are going to produce more magnetic field line in compare with 1 Tesla. Okay, and the things that you need to understand is the directions of the magnetic field always from north to south. Okay, north, south, always come up from north and then enter to the south. Okay, but it's not going to stop at south. It's going to be moving in one closed loop. Okay, so this is the difference between the charge. Like example, if you have charge, okay, if you have charge positive and negative, okay, you are going to start at positive and end up at negative. Okay, this is basically the electric field line. Okay, the difference between the magnet bar is if we have north and south, okay, it's always start from north and then go into south, but it's not going to stop at south, it's going to be in one closed loop. Okay, there's a difference between charge and also magnetic bar. Okay. Okay, so this is basically the way for you to draw the magnetic field line. Always start from north, okay, and then enter into the south, but here basically should be like one closed loop here. Okay. Okay, like I mentioned before, the earth is like one permanent magnet bar. Okay, but the things that you need to understand here is we have geographic north pole, which is basically a true magnet, or we have another one we call as the magnetic pole. Okay, so the things that you need to understand here is, example, if you use compass, okay, and then you suddenly see that the needle is basically pointing to the north, what happened is the true direction of the north is not magnetic north, is going to be magnetic south. Okay, the reason is because of north always attract to the south. Okay, seems like south always attract to the north. Okay, and that's the reason why the magnetic north is going to be opposite with the true direction, which the true direction is going to be geographic south. Okay, so you can actually see from here, okay, the difference is, okay, one difference between magnetic and also geography, the magnetic is not going to be exactly placed at the axis of rotations of the earth rotations. It's going to be a slightly difference there, where we call this one as the magnetic declination. Okay, magnetic declination, and this magnetic declination always be from 0 degree until 20 degree. Okay, so example, if you use compass, okay, you need to include this 0 to 20 degree in your calculations, then you are going to get the correct direction. Okay. Okay, and then like I mentioned before, the geographic pole is going to be different with the magnetic pole, which you can actually see from here. Okay, when you have a geographic north pole, it means that the magnet bar are going to be at the south. Okay, because it's basically aligned with the concept, which is north are going to be attract to the south, or south going to attract to the north. Okay, same goes as this one. When you have the magnetic south pole here, it means that this direction is a north magnetic bar. Okay. Okay, let's discuss about electric current and the magnetic field. Okay, so the first one that found this concept of electric current and magnetic field is Oersted. So Oersted found it by experiment, where there's a one long wire, okay, and then there's a compass that actually placed around this wire, and once Oersted turn on the power supply, there will be a current flow. Once the current flow inside the wire, Oersted realized that the needle of this compass is deflected into some direction, and then Oersted conclude that the electric current can actually produce a magnetic field. Okay. So as you can see there, the needle is deflected because of what? Because of there are some force that cause this needle to be deflected. Okay, so the directions of needle is basically the directions of the magnetic field. So how to decide the directions of the magnetic field? We can actually use the first right hand rule. Okay, the first right hand rule is consists of thumb and the finger, which means thumb is going to be the directions of the current, and the finger on all the four fingers going to be the directions of the magnetic field. Okay, so you are going to use your thumb as a current, but it can be changed. It can be current, it can be magnetic field, depends on the questions. Okay, it depends on the information given, and then this one also can be changed into current and also magnetic field. Okay, it depends, but here we are going to use this one as a current, okay, and all these four finger as a directions of magnetic field. So example, if your current moving upward, okay, so what happen is your magnetic field are moving in the counterclockwise motion. Okay, and if your current moving downward, okay, and your magnetic field are going to move in the clockwise motion. Okay, so it seems like you hold something, and that's how you actually decide the directions of the magnetic field, based on the current given, based on the direction of the current given. Okay. Okay, I already show you how to use your thumb and your finger to decide the directions of the magnetic field or current. Okay, let's proceed to the next one. Okay, so before this we talk about current and also magnetic field, which means that the current can actually produce a magnetic field. Okay, Oyster turn on the power supply. There's a current flow inside the wire and the needle deflected. Okay, what the cause of this needle to be deflected? Definitely is because of a existence of force. Okay, existence of force. Okay, so it's actually a magnetic force. Okay, so we can actually use the concept of Newton's third law, okay, where if there's a current flow, the needle are going to be deflected, which means that the current can produce a magnetic field. So based on Newton's third law, there will be action and reaction. So we can actually conclude also that the magnetic field can produce a force to the current carrying wire. Okay, Newton's third law. Okay, before this, current can actually produce a magnetic field which cause the needle to be deflected, produce a force. Okay, and based on Newton's third law, it means that the magnetic field can also produce a force to the current carrying wire. Okay, so we are going to look at how to find the directions of the magnetic force based on the current and also the magnetic field given, and also what is the factor that are going to affect the magnetic force. Okay, so the magnetic force are going to be affected by the magnetic field strength, okay, and also the current flow inside the wire, and also affected by the length of the wire exposed to the magnetic field. So example, if you have like 50 centimeter of wire and there's only 10 centimeter that exposed to the magnetic field, these 10 centimeter are going to feel some magnetic force. Okay, and then this is basically the original formula. Okay, but as you can see that, okay, so example, if you have like one wire, okay, and there's a magnetic field here, okay, magnetic field here is going to move to the east. Okay, so this inside wire we are going to have some current flow. Okay, for us to get the maximum magnetic force, it means that the wire should be, or the magnetic field should be perpendicular to each other. Okay, so example, if you have something like this is your B, okay, and then you have a current carrying wire. Okay, so what happened is you are going to get this one at the F maximum. Okay, and then how you are going to use this picture to get a maximum magnetic force. Okay, so it means that whether, okay, you are going to resolve the current carrying wire or you are going to resolve a magnetic force. Okay, example, if I want to resolve the current carrying wire, for me to get the maximum value, okay, so basically this is magnetic field. Okay, and then there's a current carrying wire in this directions. Okay, this is current flow. Okay, so the things that you need to understand here is the current, the wire should have a current flow, then definitely the wire going to feel some magnetic force. Okay, so if I am going to resolve the wire, so it means that it should be like this and like this. Okay, so this is going to be the current carrying wire, which means that this is going to be I sine theta, okay, based on the angle between the current and also magnetic field. Okay, like this. Okay, and this is going to be I cos theta. So for me to get the maximum value, definitely I need to use the I sine theta. Okay, same goes if I want to resolve magnetic field. Okay, so here I'm going to get like this and like this. Okay, so basically the angle should be like this one, so the magnetic field going to be B sine theta and this one should be B cos theta, and that's the reason why you are going to get the formula for this is F equals to BIL sine theta. Okay, so the theta will be the angle between the magnetic field and the current. Okay, so for you to get the maximum magnetic field, the maximum magnetic force, definitely the current carrying wire should be perpendicular to the magnetic field like this one. Okay, but if you want to get if you want to get the minimum magnetic force, which is definitely going to be 0, it means that the wire, okay, the wire, okay, should be parallel with the directions of the magnetic field. Okay, so this one you are going to get the minimum, which is going to be 0 Newton. This one you are going to get the maximum magnetic force. Okay. Okay, now I'm going to show you how to use the second right hand rule for you to find the magnetic force, or it can be to find the magnetic field or current. Okay, so we are going to use thumb, second and the third finger. Okay, so what happened is your thumb going to be the directions of the magnetic force. Okay, the second finger going to be the directions of the current, and the third one here going to be the directions of the magnetic field. So you can actually see that, okay, here, okay, you can see that this three finger is basically perpendicular to each other. Okay, which means that the concept is correct. Okay, magnetic field, magnetic force, and also current perpendicular to each other. Okay, so let's try with the first diagram. Okay, so the current is basically flow which is away from us. Okay, and the directions of the magnetic field going to be, this is, okay, the inner one going to be north, the outer one going to be south. So you need to make, yes, okay, to make it opposite like that. Okay, and then, okay, so which is directions of the magnetic force, which is downward. That's why you are going to get the directions of magnetic force will be downward. Okay, okay, let's try with the second diagram. Okay, the current flow is toward us. Okay, so you are going to like change like that, so it's toward us. Okay, okay, and then the directions of the magnetic field is correct from north to south. Okay, so north to south, so your directions of magnetic force will be upward. Okay, okay, so that's how you use the second right hand rule, okay, to find the current, or it can be magnetic field or magnetic force. Okay, okay, so we already know how to find the directions of the magnetic force, and for the magnitude of the magnetic field we can actually use F equals to BIL sine theta. Okay, like I mentioned before, for you to get the maximum magnetic force, your wire, or definitely current, should be perpendicular to the magnetic field, and for you to get the minimum, which is your magnetic force is 0, the wire carrying current, okay, should be parallel to the magnetic field. Okay, okay, okay. So the things that you need to understand here is the magnetic field are going to be the unit is going to be Tesla. Okay, and there are certain questions, the magnetic field they are going to give you in terms of Gauss, which is 1 Gauss. Okay, so 1 Gauss is basically equivalent to 1 power of -4 Tesla. Okay, before you proceed with the calculation, make sure that your magnetic field always be in Tesla. If example the question give you in Gauss, change that into Tesla first. Okay, okay. Okay, there are certain symbols that we are going to use to represent the electric current or the magnetic field. So it can be cross or it can be dot. Okay, so basically this cross and dot is come from the arrow. Okay, so arrow is something like this. This is basically like a tail. Okay, and then example, if you observe at these directions, okay, okay, so what happens is you are going to look at the tip of the arrow, okay, which is going to be like this symbol. Okay, okay, so it means that it's going to point towards you. Okay, so this one is basically to represent that it's away from us, which is we are going to look at this part, which is away from us. Okay, so this symbol can be represented as an electric current or a magnetic field, depends on the information given. Okay, okay, so this is one of the questions which is quite easy. Okay, so the question asks you to find the magnitude of the force. Okay, so they already give you the length, okay, which is in centimeter. Make sure that you always change that into SI unit, and then the pole face of the magnet, which is at the angle of 60 degree. Okay, the magnetic field is approximately uniform at 0.90 Tesla. Okay, so the angle is basically between the current and also the magnetic field. Okay, so you can actually use the formula of F equals to BIL sine theta. Okay, So it's going to be F equals to BIL sine theta. Okay, so the B going to be 0.90 Tesla and the current is 30 ampere. And the length is 0.12 and the angle should be sine 60 degree. Okay, so you are going to get your answer is 2.81 Newton. Okay, let's proceed to the next one. Okay, so example, if you have a question like this, okay, the first thing that you are going to look at is the length of the wire that exposed to the magnetic field, which you can actually see that only this part and this part and this part going to feel a magnetic force because this is the length that is exposed to the magnetic field. Okay, and then there's a current flow. Okay, make sure that there's a current flow inside the wire, then definitely that wire are going to feel a magnetic force. Okay, so first thing first, when you encounter this kind of question, you are going to decide the directions of the magnetic force. The reason why we need to find the directions of the magnetic force is because to determine whether it's going to be negative or positive. Okay, so example, if you didn't know yet the directions of the magnetic force, so this one example you need to find it by yourself. Okay, so we are going to look at this part first, which is at this one. Okay, so I'm going to show you how to use the second right hand rule to decide the directions of the magnetic force. Okay, so now the symbol of the magnetic field is towards you, or you can actually say that out of the page. So I'm going to do like that. Okay, so this is my magnetic field, which is out of the page, and the current is pointing downward, or you can actually say that it's pointing towards you. So it means that the magnetic force are going to be to the left. Okay, now we are going to do for the green one that I circled already. Okay, so now the current is moving away from you. Okay, and the magnetic field is in the same direction, which is out of the page. Okay, or maybe pointed towards you. Okay, so you can actually see that the magnetic force here are pointing to the right. Okay, so hopefully you understand on how to use the second right hand rule to find the magnetic force. Okay, so now we are going to find the magnetic force for this part. Okay, so we are going to use the same concept. Okay, so now you have your directions of the magnetic field, which is away which is out of the page, and the current there going to be to the right. Therefore your force are going to be towards you. Okay, so that's directions of the magnetic force. Now we are going to find the magnitude of the magnetic field. Okay, the first thing that you need to do is you need to find whether the force can be cancelled out or not. Okay, because the force here is to the left and this one to the right, therefore the net force for this one going to be equals to 0. Okay, so the only left force is going to be in this direction, which is towards you. Okay, so that one are going to be the one that have a magnetic force. So we can actually use F equals to BIL sine theta. Okay, your magnetic field and your current is perpendicular to each other because your current in this direction and your magnetic field going to be vertical. Okay, and that's the reason why it's going to be sine 90. Okay, which is equivalent to 1. Okay, so now the question asks you to find B. So B equals to F over IL. Okay, so the force is going to be 8.48 power of negative 2, and then the current going to be 0.245, and your length here is only 10 centimeter, which is going to be 0.1. Therefore you are going to get your answer is 1.42 Tesla. Okay, that's how you do it. Make sure that you only find the length of the wire that have a current, they're going to expose to the magnetic field. Okay, but once you find the magnetic force, if example they are going to be in the different direction, therefore the net force they're going to be 0. Okay, so we are going to do for this kind of question. Okay, so now the question asks you to find the magnitude and the directions of the force that the magnetic field exert on the wire. So you can see that the only place that have a magnetic force is going to be in this part only. Okay, so now first thing first, we are going to find the magnetic force. Okay, the directions of the magnetic force first. Okay, so if example for this one, okay, this one blue one, and this one I'm going to put it as a green one. Okay, so I'm going to show to you how to use the second right hand rule for you to find the directions of the magnetic force. Okay, so we are going to start with the blue circle. Okay, so the magnetic field is out of the page, or you can actually put it as a in towards you. Okay, and the directions of the current is to the right. Okay, so I'm going to put like this, so you can actually see that the magnetic force is going to point it downward. Okay, so now we are going to find the directions of the magnetic force for the green one. Okay, so the current the magnetic field, the magnetic field going to be towards you. Okay, and the current is upward. Okay, so what happened is your magnetic force is pointing to the right. Okay, so that's how you use your second right hand rule for you to find the magnetic force. So based on the one that I already showed you how to find directions of magnetic force, so this one going to be downward, this one also downward, because the directions of the current and the magnetic field in the same direction, and this one going to be to the right. Okay, the things that you need to understand here is this is basically pointing downward, this is downward, which is in the y component, and this one is pointing to the right, which is in the x component. Therefore, x and y you need to use, therefore because we have a magnetic force in x and y, we need to use a vector, which means that we need to find the magnitude based on Pythagoras theorem. Okay, so we are going to start with the directions of the y component first. Okay, so means that I'm going to put it as a fy. Okay, fy, which is going to be bil sine theta. Okay, so the b going to be 0.240, and the current going to be 4.50. And how about the line? Okay, because this one plus with this one going to be equals to 60 centimeter. Okay, because that is the part that can feel a magnetic force. Okay, so you are going to put as a 0.6 over there. Okay, and then sine 90 degree. Okay, because the current is in that directions and the magnetic field in that direction, therefore it's going to be perpendicular to each other. Okay, so you are going to get that is 0.648 Newton. Okay, then we are going to do for the x component. Okay, so the fs, which is pointing to the right, so it's going to be 0.240, and the current is 4.50, and the length is 30 centimeter, which is going to be 0.3 sine 90. So you are going to get that is 0.240 times 4.50 times 0.3. You are going to get 0.324 Newton. Okay, because we need to find the magnitude and direction, therefore we need to use the Pythagoras theorem, which means that we are going to find only f, which is fx squared plus fy squared, which is going to be 0.324 squared. Okay, plus with the 0.648 square. Okay, 0.648 square, square root everything, so you are going to get 0.724 Newton. And the question asks you to find the direction. Okay, therefore we need to use tangent theta. Okay, tangent theta, which is fy over fx, which means your fy is 0.648 and your fx is 0.324. Okay, therefore your angle here you are going to get 63.4 degree. Okay, because based on the directions of the magnetic force that we use the second right hand rule, so we are going to get that is to the right and downward. Therefore the directions of the magnetic force going to be in this direction. Okay, so this is 63.4 degree, and this the magnitude is 0.724 Newton. Okay, or you can actually say that is going to be south of east. Okay, Okay, so we are going to answer second question. Okay, so now we are going to start with the first one, A. Okay, what is the magnitude of the magnetic force on the 130 centimeter side? Okay, definitely the answer going to be 0. Okay, the reason is because the directions of the magnetic field, which is this one, and the directions of the current in the same direction. Therefore, it's going to be F equals to BIL sine 0 degree, which is you are going to get your force is 0 Newton. Okay, question B. What is the magnitude of the magnetic force on the 50 centimeter side? Okay, so when you have this kind of question, the first thing that you are going to do is you are going to use the second right hand rule for you to find the directions of the magnetic force. Okay, which means that the current is going to be to the left. Okay, and then the magnetic field going to be like almost like 45 degree. Okay, like that, and then therefore you are going to get your magnetic force, which is going to be out of the page. Okay, so we are going to find the angle which is between the magnetic field and the current. Okay, so our current is going to be in that direction and the magnetic field going to be in that direction, so the angle going to be here. Okay, so for you to find the angle here, the first thing first you are going to do is you are going to find the theta here. Okay, the theta here going to be 67.38 degree. Okay, so means that if I draw it here, you are going to have this one, which is this is going to be 67.38. Okay, which means that I can actually say that this one, this pipe is going to be 22.62 degree. Okay, so this is like a mirror, so this one also 22.62 degree, and this one going to be 90. So it means that the angle between I and B going to be 112.62 degree. Okay, so you are going to use the same formula, which is F equals to BIL sine theta. So the B going to be 75 millitesla. Okay, and the current there is going to be 4, and the length there going to be 0.5, and the angle is sine 112.62. Okay, so you are going to get this one is 0.138 Newton, and the directions of the magnetic force is out of the page. Okay, if the question asks you about direction, but it's better for you to give the direction, because we are going to use that to help us answer the question D. Okay, so now we are going for C. What is the magnitude of the magnetic force on the 120 centimeter side, which is this one? Okay, so means that, okay, first thing first, we are going to draw it first. Okay, so this is your current and this is your B. So this is the angle that you need to find, which is we already find for this part is 67.38. Okay, so if I separate like that, I'm going to get this one is 67.38. Okay, so I'm going to get here is 67.38. Okay, so this is going to be 90, which is 90 plus 67.38. Therefore you are going to get is 157.38 degree, which is the angle between current and the magnetic field. Okay, so we are going to find the force over there. Okay, so we are going to use F equals to BIL sine theta. Okay, so the B going to be 75 negative 3. Okay, and the current is 4. Okay, and the length is 120 centimeter, which is 12. Okay, and then you are going to use sine 0.38 degree. So you are going to get here is 0.138 Newton. And how about the directions? Okay, for the direction you need to use the second right hand rule, which is, okay, current is pointing upward and the magnetic field is going to be in that direction. Okay, so you are going to get is the which is into the page. Okay, so we're going to get here is into the page. Okay, so for the D, what is the magnitude of the net force on the loop? So you need to add up everything. Okay, so the first one, A, is 0. Okay, D, 0. Okay, the second one is out of the page. Okay, you can actually decide by yourself whether out of the page is negative or into the page is negative. Okay, so I'm going to put out of the page as a positive. Okay, and then into the page here as a negative. Okay, therefore my net force going to be 0 Newton. Okay, so that's how you do it. Okay, now we are going to talk about the force on electric charge. Okay, because we're talking about current flow, definitely there will be a electron flow. So here you are going to find a magnetic force acting on the charge. Okay, but before I'm show to you how to use the second right hand rule for electric charge, we are going to find the magnitude of the force acting on electric charge. Okay, because because charge is moving through some distance, so we know that the velocity going to be length over time. Okay, because the charge is moving through some distance with time. Okay, therefore you are going to get that one as a velocity. Okay, and as we know that the relationship between current and also charge is going to be charge per unit time. Okay, but example, if you have a lot of charge, you need to put number of charge here. Okay, so we are going to put this equation. Okay, but this one are going to put subject as a L Vt. Okay, we are going to put it inside F equals to BIL sine theta. Okay, so the B here, so I going to be NQ over T, but I'm going to change the Q to the small q. Okay, QT. Okay, and then for the L going to be VT. Okay, so you can cancel T, therefore you are going to get your equation is NQVB sine theta. Okay, so the angle theta here are going to be between B and also velocity. Okay, so this is how for you to get the magnitude of the magnetic force acting on the charge. Okay, now we are going to proceed with the directions of the magnetic force. Okay, for the directions of the magnetic force acting on the charge is basically same as the force acting on the wire carrying current. Okay, so but you are going to change one finger here. Okay, before this is B, this is force, I current, and B the magnetic field. Now you are going to change this current to the velocity. Okay, but the things that you need to know here is the second right hand rule can only be used for the directions of the conventional current flow, which is from positive to negative. Okay, example, if you need to find the directions of the magnetic force for electron or any negative charge, you need to change that V to the opposite direction. Okay, example, if the question state the electron is moving to the right, okay, electron moving to the right, because this second right hand rule is for conventional current flow, therefore if it's moving to the right, then you are going to put it moving to the left. Okay, so this you need to change the direction only for electron or any negative charge. Okay, but this one you can use the original right hand rule for positive charge or proton. Okay, let's proceed to the next. Okay, so we have like one question here. Question asks you about a negative charge is placed at rest near a magnet. Okay, will the charge begin to move? Will it feel any force? What if the charge we change that into the positive Q? Okay, because the question state that is placed at rest, therefore there is no any magnetic force. Okay, because you need to understand that for you to have a magnetic force, therefore you need to have a move, therefore your charge need to move. Okay, if example at rest, it means that there are not going to be any magnetic force. Okay, so let's proceed to this one. Okay, so now the question asks you to determine the magnitude and direction of the magnetic field in this region. Okay, the question already state that a magnetic field exerts a force 14 Newton toward the west, okay, on a proton moving vertically upward. Okay, when moving horizontally in a northerly direction, the force on the proton is 0. Okay, So you can actually find the directions of the magnetic field in two ways. Okay, one is you can actually find the answer based on the question given, because the question state that when the charge moving horizontally in the northerly directions, okay, so this charge is moving in that direction, okay, so the force on the proton is going to be 0. Okay, so you need to understand that what is the requirement for the force to be 0. It means that the magnetic field, okay, and the velocity is in the same direction. Therefore, our directions of the magnetic field going to be to the north, okay, pointed to the north. Okay, or you can actually use second right hand rule, because the question state that the force is toward the west. Okay, okay, and then the velocity is moving upward. Okay, therefore you can actually see that your finger that represent magnetic field is away from us, or you can actually say that point toward the north. Okay, so is there for this question you can actually find the magnetic field using two methods. Okay, using the information given, or you can actually use the second right hand rule. Okay, now we are going to find the magnitude of the magnetic field. So we have equation of F equals to Q VB sine theta. Okay, and the angle there definitely going to be sine 90, which is 1. Okay, so F is 8 negative 14. Okay, and the charge is a proton, which is 1.602 power of negative 19. Okay, if example this is for electron, you need to change the directions of V, and please do not put any negative in the calculations. Okay, okay, and then the velocity is 5 power of 6. Okay, B we didn't know, and the sign going to be 90 degree. Therefore, for the B, you are going to get 0.10 Tesla. Okay, that's how we do it. Okay, so I'm going to show to you how to use the second right hand rule for you to find the directions of the magnetic force, because the question asks you the deflection of the charge, which means that that one is for the magnetic force. Okay, but the things that you need to remember here is this original directions of the right hand rule is for conventional current flow. By example, if you have like electron or any negative charge, the directions of the velocity need to be opposite. So example, if the question give you to the right, therefore you need to change the velocity to the left. Okay, so we are going to start with the question A. Okay, there is going to be the positive charge, and the magnetic field is into the page. Okay, and then the velocity is to the right, therefore you can actually see that the magnetic force is away from you. Okay, so the answer is going to be away from you. Okay, for question B, okay, there is electron. Okay, the velocity in the diagram show is to the left, therefore you need to change that to the right. Okay, and then for the magnetic field is pointed upward, therefore you can actually see that the magnetic force is towards you. Okay, for question C is obviously show that the directions of the magnetic field and the directions of the velocity is parallel to each other, therefore it's going to be 0 Newton. Okay, okay, for question D, there is positive charge and the velocity is upward. Okay, and the magnetic field is like pointing 45 degree like that. Okay, so you can actually see that the directions of the magnetic force is going to be away from you. Okay, okay, so that's how you do it. Okay. Okay, now I'm going to show to you how to find the magnetic force using the second right hand rule. So we are going to start with the question A. Okay, so there is positive charge, which is the directions of the velocity is to the left. Okay, and then the magnetic field is into the page, therefore the magnetic force is going to be towards you. But it's better for you to give your answer, which is at the positive z-axis. Okay, example, if you have any questions that already state the axis, it's better for you to give your answer in terms of axis. Okay, so you can see that it's towards you, or it's better to put that as a positive z-axis. Okay, okay, for the question B, the directions of the magnetic field is away from you. Okay, but this is electron, which means that the velocity is going to be upward. Okay, the diagram should downward, but for the electron you need to change the directions of the velocity, which is upward. upward, okay, and then the magnetic field is like away from you, so it means that the directions of the magnetic force is going to be at the negative axis. Okay, okay, okay. For question C, okay, is obviously show that the magnetic field and the v and the velocity is parallel to each other, therefore the answer going to be 0 Newton. Okay, so that's how you do this kind of questions. Okay, okay, let's proceed to the next one. Okay, so example, if we have a velocity that moving to a plane of magnetic field, what happen is these charges are going to move in a circular motion. Okay, so the directions of the electron or proton, clockwise or anti-clockwise, is depends on the directions of the magnetic field given and the directions of the velocity given. Okay, so now I'm going to show to you how to find the directions of the magnetic force. Okay, based on our understanding, if example the object is moving in circular motion, definitely the magnetic force should be pointed toward the center. Okay, and the things that you need to understand here is even though the velocity is constant, but there's still acceleration because of change of direction. Okay, so you are going to find the magnetic force for the first picture. Okay, the electron. Okay, so the velocity is pointing to the right, but because electron we need to put it to the left. Okay, and then the magnetic field is into the page. Okay, so you can actually see that the magnetic force is going to be towards me, which is basically from the diagram it says is going to be towards the center. Okay, so example, if you change into the second one, which is velocity in some degree, so the velocity is going to be like that, so still the force is always pointed inward, which is pointed toward the center. Okay, okay, so for the second diagram, which is for the positive charge, okay, the velocity is to the left. Okay, and then the magnetic field is into the page, therefore you can actually see that the magnetic force is away from me, which is basically from the diagram itself is going to be toward the center. Okay, so if I change the velocity with some degree, it's still toward the center. Okay, so you can actually conclude that the directions of the electron is going to be in clockwise motion, but the directions for the positive charge going to be in the anti-clockwise motion. But this one is depends on the directions of the magnetic field and the directions of the velocity given by the questions. Okay, okay, let's proceed to the next one. Okay, so this is basically the way for you to find the directions of the magnetic force. Okay, but the things that you need to understand here is if the velocity is moving to the plane of the magnetic field, which is like this, so what happened is the charge going to move in the circular motion. And the things that you need to understand here is if the force is perpendicular to the velocity, definitely is moving in the circular motion. Okay, okay, now we are going to relate the concept of centripetal force with the concept of force acting on a charge. Okay, so we know that force acting on the charge is going to be F equals to Q VB sine theta, and because it's relate with the concept of centripetal force, we can actually put this force as a mv square over r. Okay, so if example, if you need to find the radius, so it's going to be, okay, v sine theta. So because this one can be sine 90 degree, the reason is because the for the charge to move in circular motion, definitely the velocity and the magnetic field should be perpendicular to each other. Okay, okay, so v here can be cancelled out. So for you to get the radius means that you should get qb over mv. Okay, so that's how you do it. Okay, but the things that you need to understand here also, because we discuss about the concept of moving in circular motion, therefore we need to relate with the frequency and also the period. Okay, so as we learn this frequency and period in the physics 1, so you can actually say that for you to find the period, which means that it should be t equals to 2 pi r over v. Okay, this formula is basically get from velocity, length over time, and because we're moving in circular motion, that's why this one we need to change to 2 pi r. Okay, and because we're talking about period is basically for time for you to complete one revolution. That's the reason why we need to change this one into capital T to represent that it's going to be period. For small t is going to represent time. Okay, and then because we talking about period, definitely we need to talk about frequency, which is frequency equals to 1 over period. That's how you derive it. Okay, now we are going to answer some questions related with the concept of circular motion and also force acting on the charge. Okay, so this one, the question already give you the velocity and then also give you the magnetic field. So you can actually use the formula that already derived. Okay, so it's basically mv square over r equals to qvp, because this is both force. Okay, so the v can be cancelled here, so you are going to get your radius is qb over mv. Okay, because this is electron, so therefore you are going to use 1.602 power of negative 19. Okay, and the magnetic field is 0.010 Tesla divided by the mass of electron, which is 9.11 power of negative 31, and the velocity is going to be 2 power of 7. Okay, so you are going to get this one, the radius is going to be 1.1 power of negative 2 meter. Okay, okay, let's proceed to the next one. Okay, so the question asks you, this is a conceptual question. So the question asks you, can a magnetic field be used to stop a single charged particle as an electric field can? Okay, like I mentioned before, electric field is basically in the directions of the velocity. Okay, therefore for this one, the electric field can produce a force that going to stop the charge. However, when it comes to the magnetic field is basically perpendicular to the directions of the velocity. Therefore, this magnetic field cannot produce any magnetic force to stop a charge that is basically the directions, but that same direction with the velocity. But the magnetic field can produce a magnetic force on the charge that actually move, which is perpendicular to the magnetic field and perpendicular to the velocity. Okay, so this is one of the questions, like conceptual question also. Okay, the question is ask you, which of the three path 1, 2, 3 does the particle flow, and this particle is negative charge. Okay, so because the velocity here is pointing to the right, okay, and like I mentioned before, you need to change your velocity to the left, because the second right hand rule is for conventional current flow, and then the conventional current flow is opposite with the electron flow. Okay, and then the magnetic field is into the page, therefore you can actually see that the directions of the magnetic force is going to be downward. So it means that the negative charge here are going to be deflected downward. Okay, so this is the questions 5. Okay, the question asks you to find which magnetic field is stronger. Okay, so for us to find which magnetic field is stronger, we are going to derive the formula. Okay, because we are going to look at the radius, because you can see that this one and this one, they have different radius. So we are going to find the relationship between radius and magnetic field strength. Okay, so so we are going to derive the formula, which is F equals to QVB, which means that this is going to be mv square over r QVB. Okay, so V here. Okay, so you put the magnetic field as your subject, which means that you are going to get mv over qr. Okay, which means that large radius are going to produce produce small magnetic field, and small radius are going to produce large magnetic field. So definitely the answer going to be B1, because B1 have a smaller radius in compare with B2. Okay, so question B. Okay, because as you can see that based on our understanding, if example the charge is moving in circular motion, it means that the force is always toward the center. So we can actually see that the force here is toward the center, and this also toward the center. Okay, so you can actually use the second right hand rule for you to find the directions of the B1 and the B2. Okay, so the force is toward the center, so I put my force to the left. Okay, and the velocity here is downward, but because this one is electron, therefore you need to change the directions of the velocity, which is upward. Okay, therefore your magnetic field for B1 going to be away from you, okay, away from you, or you can actually say that as a into the pitch. Okay. Okay. And for question B2, the same thing. Force is toward to the right, okay, but this is electron, okay, electron moving downward, but the directions of the velocity for your hand going to be upward. Okay, so your directions of magnetic field is going to be towards you. Okay, or you can actually say that as a out of the pitch. Okay. Okay, so the question D is the time span in region 1 is greater than, less than, or the same as the time span in region 2. Okay, so we can actually derive the formula for this one for us to find the relationship between the velocity and also the radius. Okay, so as we know that V equals to 2 pi r over t. Okay, so based on the equations, we need to relate that also with the magnetic field. Okay, so from this one, okay, so we need to find the relationship between the B magnetic field and also the period. Okay, so you put this one as the subject with the V as the subject, which is going to be QRB over M, and then you put it inside this formula. Okay, so you are going to get here is QRB over M, which is 2 pi r over t. Okay, so T going to be 2 pi 2 pi m over QB, which means that increase of magnetic field, decrease of T. Okay, so now the question asks you to find the time span in region 1 is greater, less than, or the same as the time span in region 2. Okay, from the previous question, the B1 have the strong magnetic field. Okay, therefore the time there is going to be reduced, which means that the time span in region 1 going to be less than region 2. Okay. Okay, so this is like the summary on how to use the second right hand rule. So we have the first right hand rule and we have the second right hand rule. So the first right hand rule is basically involve thumbs and also four fingers, which is you need to find the directions of the magnetic field based on the current given, or you need to find the directions of the current based on the magnetic field given. Okay, and then we have the second right hand rule, which we can actually use that for force on electric current, or we can actually use that on the electric charge. Okay. Okay, let's talk about the last part, which is going to be torque. Okay, before we move on with the torque here, we need to understand what does torque mean. Okay, torque means the tendency of the force to produce to produce a rotational motion, or we can actually say as a circular motion about an axis or a point, about an axis or a point. Okay, you can actually say that your axis is like fulcrum. Okay, so means that, or hinge. Okay, like example, you can see from the door, okay, you have a hinge there, so the hinge are going to be acting as the axis. Okay, so example, if you apply force, okay, example, I put it, this is a hinge. Okay, this is a hinge. Okay, and you apply force perpendicular to the level arm. Okay, the level arm going to be this one. This is level arm. Okay, the level arm is basically from hinge up until the force that you need, up until the force that you apply. Okay, that is we call as a level arm, which is represented by D. Okay, so when you apply force perpendicular to the level arm, which you can see that perpendicular to the level arm, what happened is these beam are going to move in a rotational motion. Okay, so that's the reason why torque is basically the formula going to be force perpendicular with the D. D is a level arm. Okay, so you need to find the force that perpendicular to the level arm, therefore you can actually produce torque. Okay, another name for torque we call it as a moment. Here represented by capital M. Okay, so now we have like one closed loop, and this closed loop are going to produce a movement that is circular motion. Okay, but mostly for this kind of question, the question going to ask you the directions of the loop, whether it's going to move clockwise or anti-clockwise based on the current and the magnetic field given. Okay, but before we proceed with the directions on how to find the directions of whether it's moving clockwise or anti-clockwise, we are going to derive a formula for torque. Okay, so Example, if we have like one closed loop, okay, and this closed loop have axis in the y directions, okay, so it's going to move like clockwise or anti-clockwise like this. Okay, so example, if I put this length as b and this length as a. Okay, so first thing first, I'm going to derive the formula before we actually find the directions of the magnetic force. Okay, so example, if your magnetic field is in this direction, okay, so means that the only part that going to feel a magnetic force is going to be this one and this one. Why? Is because this loop have a current, and this current is basically perpendicular to the directions of the magnetic field. Okay, so for this part and this part, there will be no magnetic force because the current flow is in the same direction of the magnetic field. Okay, so example, if I put the current flow like this, sorry, should be this and like this. Okay, so for you to find the torque, okay, we know that for formula of torque equals to force multiplied by the level arm. Okay, D is the level arm, which is from the hinge or axis up until the force applied. Okay, so like I mentioned before, this part can produce force and can produce force. Okay, therefore the D there going to have in this direction and in this direction. Okay, in this part and in this part. Okay, so it means that for me to derive the formula, it should be torque equals to, example, this is number 1 and this is force number 2. Okay, so the force is basically the same value because you have a same current, same magnitude of magnetic field. Okay, so based on this one, because we talk about current which is flow inside the wire, so we can actually use BIL sine theta. Okay, and our level arm here is going to be this one and this one. Okay, that's why B need to divide by 2. Okay, because we have two force which is at this part and at this part. Okay, the directions of the magnetic force going to be decided later. Okay, now we are going to derive the formula first. Okay, so torque going to be equals to B. Okay, and the I and the L here going to be the length of A. Okay, and the level arm here should be B divided by 2. Okay, here this one is level arm. Okay, from here to here. Okay, so you can see that this is the level arm. Okay, and then because we have two force there, definitely we need to put another one, which is BI A B over 2. Okay, so when we add up these two, so we are going to get is BIAB. Okay, because okay, like this one, this is like one loop. Example, you have like a lot of loop, therefore you need to put number of loop here. Okay, so the A times B, which is this one. Okay, this is A and this is B, and definitely that one going to give you area because one side multiplied by another one side. Okay, A times B. Okay, so you are going to get this one is NIAB. Okay, and then if example you have need to put sine theta because the original formula have a sine theta, I forgot to put it here and here. Okay, the theta here is going to be the directions of the magnetic field and the normal to the area, not area, normal to the area, which is always be perpendicular to the surface. Okay, example, if you have like this surface, so means that the normal to the area is going to be this one. Okay. So that is the way for you to find the formula for torque. Now we are going to find the directions of the magnetic force, whether it's moving clockwise or anti-clockwise. Okay, so I'm going to so example, if you observe from this side, so means that you are going to look the current here like a dot because it's pointing towards you, and this side you are going to see the current here are going to be away from you. Okay, so this is like one line here. Okay, so this is the axis. Okay, and then the magnetic field is in that direction. Okay, so for you to find the magnetic force, okay, so you are going to use the second right hand rule. So means that for you to find the directions of the magnetic force, okay, based on the picture that I have drawn it for you for this one, which is for this one. Okay, so okay, Okay, so the current is towards you and the magnetic field is to the right. Therefore, the magnetic force here are going to be upward, like that. Okay. Okay, for the cross one, the current is away from you and then the magnetic field is to the right. Therefore, the magnetic force is going to be downward. Okay, so the directions of the torque going to be clockwise or anti-clockwise? Definitely is going to be clockwise motion because it's moving in this direction. Okay, so that's how you do it. Okay, so it depends on the directions of the magnetic field and the current. Okay. Okay, so another things that you need to understand here is we have one terms we call as the magnetic dipole moment. Okay, based on the name itself, magnetic dipole moment. Dipole, it means that opposite. Okay, because the current one is towards you and another one is away from you, and that's the reason why we call as a dipole. Dipole means opposite. Okay, or example, you can actually say dipole charge. It means that one negative charge and one positive charge. Okay, moment is because the other name for torque is moment. Okay, so for magnetic dipole moment, which is represented by mu. Okay, so how to use this mu is before this we derive our formula is torque equals to NIAB sine theta. Okay, mu is basically NIA, which is number of loop multiplied by current multiplied by area. Okay, so we are going to get mu times B sine theta. Okay, so mu is NIA. Okay, so for you to decide the directions of mu or magnetic dipole moment, you need to use the first right hand rule. Okay. Okay, so now I'm going to show to you how to use the first right hand rule for you to find the magnetic dipole moment. Okay, so this forefinger going to be the directions of the current, so it's going to be anti-clockwise or clockwise, depends on the information given. Okay, and the thumb going to be the directions of mu or magnetic dipole moment, which is also the directions of the normal to the area. Okay, because like I mentioned before in the chapter 3, the normal to the area always be perpendicular to the surface. So it can be like this, it can be like this. So which direction is correct for the normal to the area? So it depends on the direction of mu. Okay, so example like I'm draw it to you. Okay, so that now the directions of the current is anti-clockwise motion, which means that when you put it like this, you can see that the mu is pointed towards you. So this is also the directions of the normal to the area. Okay, so you can actually use the first right hand rule for you to find the directions of the mu. Okay, but please make sure then before you proceed with the calculation, please find first the directions of the mu. Okay, because in your calculation, in your equation, you can see that the theta here is between magnetic field and normal to the area. Therefore, you need to find the directions of the normal to the area first before you can actually use the angle. Okay, and then use the equation given. Okay. Okay, so this one is another this is already show you how to find the directions of the magnetic force. So you can actually see that this diagram of B is basically you are going to look at this right. Okay, so your eyes is going to point towards that. Okay, so you are going to get your magnetic force is moving clockwise motion. Okay. Okay, example, you have a loop, they are going to be slanted a little bit with some angle. So you can actually see that this is the way for you to find the directions of the magnetic dipole moment. Okay, so the current flow here is going to be in anti-clockwise motion. Therefore, your directions of the dipole moment going to be in this direction, which is this is also the directions of the normal to the area. Okay. Okay, so this is the way for you to use the first right hand rule for you to find the mu, which is the magnetic dipole moment, and also the directions of normal to the surface. Okay. Okay, so we are going to test what we learned before for this question. So now the question asks you to find the maximum and the minimum torque exerted in the coil by the field. Okay, for the minimum one, you need to understand that for the minimum one, the BIL sine theta and the theta here should be 0 degree, which means that the directions of the current carrying wire, which is in the same direction of the magnetic field. Okay. Okay, and for the maximum one, definitely the directions of the current carrying wire should be should be perpendicular with the directions of the magnetic field. Okay, so for this one, you are going to use torque equals to NIAB sine theta, and because maximum, therefore is going to be sine 90. Okay, so then loop current is 3, and the area here is going to be pi r square, so it's going to be pi times times 0.2. Okay, this one going to be square, and then multiply with the magnetic field, which is 2 Tesla, and then sine 90. Okay, so you are going to get the maximum torque going to be 1.88 meter Newton. Okay. Okay, so let's try another questions. Okay, so the question asks you to calculate the current that result in the magnetic dipole moment. Okay, so they already give you the magnetic dipole moment, and as we know that formula for the magnetic dipole moment going to be mu equals to NIA. So we have 160 turns, which is 160 loop. Okay, and the current is going to be okay, we didn't know about the current. Okay, and then the area is going to be, because circular, therefore you need to use pi r square. Okay, pi r square, which is going to be times 0.9. Okay, okay, and the mu here is going to be 2.30. Therefore the current here you are going to get is 12.7 ampere. Okay, so for question B, find the maximum torque. Once the question mentioned maximum torque, definitely is going to be 90 degree, which is between the directions of the magnetic field, and the normal to the area is 90 degree. Okay, the question asks you to find the maximum torque. Therefore the coil current has experienced a uniform 35 millitesla. So as you can see that torque is basically is going to be mu times magnetic field. So mu you already have 2.3. Okay, and the B here you have 35 negative 3. Okay, and sorry, it's going to be sine theta here, which is sine theta is going to be 90 degree. Okay, so you are going to get your torque is 8.05 power of negative 2 meter Newton, or Newton meter. Okay. Okay, so this one, okay, we have one last question which is going to relate with torque. Okay, so now the question asks you to find net force and torque that the magnetic field exert on the coil. Okay, example. Okay, so I'm going to show to you how to find the directions of the magnetic force for question A. Okay, so we are going to start with the first part. Okay, so the you are going to refer for the first and second part based on the yellow diagram. Okay, so the current is pointing towards me. Okay, and the magnetic field is into the page, therefore you can actually see that the magnetic force is pointing to the right. Okay, for the second part, the current is away from you, but the magnetic field is into the page, therefore your magnetic force is pointing towards the left. Okay, and for point 3, okay, the current is to the left and the magnetic field is into the page, so your the magnetic force is going to be towards you, which is based on the red diagram is going to be downward. Okay, okay, and for the number 4 part, okay, the current is to the right and the magnetic field is into the page, and the magnetic force is away from you, or based on the diagram is going to be upward. Okay, okay, so that's how you find the magnetic force for question E. So based on the diagram, you can actually see that the magnetic force for this one going to be cancelled with this one. Okay, so the net force for the 1 and 2 going to be 0, and for the number 3 and number 4, because it's moving because the magnetic force is in the opposite direction, therefore the net force therefore there also be 0. That's the reason why for question A, the net force is going to be equal to 0. Okay, and like I mentioned before, doesn't mean that if you have net force equal to 0, doesn't mean that your net torque going to be 0. Okay, but why this one going to be 0 is because of, you can actually see that, okay, the force here is parallel, okay, with the level arm. Okay, but you need to understand that for torque to be happen, you need to make sure that the force need to be perpendicular to the level arm. Okay, so because the force is parallel to the level arm, therefore the net torque also equals to 0. Okay, 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 but the things that you need to understand here, even though this one, the force is perpendicular to the lever arm. However, because it's actually at the axis, so at the axis there will be no force. There will be the net torque going to be equal to 0, because torque for the lever arm, we are going to take it from force up until lever arm. So force here is basically on the axis of the hinge. That's the reason why torque going to be 0 for number 3 and number 4. Okay, so for question B, okay, the question say is rotated through a 30-degree angle about the axis shown, with the left side coming out of the plane and the right side going into the plane. So this one going up and this one going to be down. So example, if I'm going to look at this direction, so I'm going to get my diagram going to be like this. Okay, so this is going to be the first part and this one going to be the second part. Okay, so the angle going to be 30-degree angle. Okay, because it's rotated to 30-degree angle and this is the axis. Okay, so now we need to find the directions of the magnetic force. Okay, so you can use the second right hand rule. Okay, for the first part, okay, the current is toward us and the magnetic field is into the page. Okay, so you can actually see that the magnetic force going to be in this direction. Okay, for the second part, the current is away from you and the magnetic field is into the page, therefore the magnetic force going to be in this part. Okay, so because but this one, because the directions of the force is opposite to each other, like this one is to the right and this one to the left, therefore the net torque going to be 0 for question B. Okay, net force going to be 0 for question B. However, because the force is not parallel to the lever arm, therefore this force can produce a torque. Okay, because torque is about moving in clockwise motion or moving in rotational motion. Okay, because the force is not parallel to the lever arm, therefore it can actually produce torque. Okay, so based on the diagram itself, you can actually see them is going to move in the clockwise motion. Okay, so you need to find the magnitude of the torque, which is going to be net torque equals to, okay, NIAB sine theta. Okay, so theta. Okay, so the theta here, you are going to find it first by using the first right hand rule for you to find the directions of the normal to the area. Okay, because the current here is moving anti-clockwise motion, therefore your magnetic dipole moment when you transfer into this picture is going to be in this direction. Okay, so this is your normal to the area, which is also the directions of the mu. Okay, so okay, so your sine theta going to be between the magnetic field and also the normal to the area, and the magnetic field is away from you, which is this is the magnetic field. Okay, therefore the directions of the magnetic field, the directions of the magnetic field and the normal to the area going to be angle, it should be, okay, so the angle going to be 150 degree because it's 90 and this is going to be 60 because this is also 19, so this is 60. Okay, so it should be 150 degree. Okay, and you are going to put that inside the formula, which is a number of fluid is going to be 1. Okay, and the current is going to be 1.40 and the area is 22 centimeter multiplied by 35 centimeter, which is 0.22 multiplied by 0.35. Always change into SI unit. Okay, and the magnetic field going to be 1.50 and the sine there is going to be sine 150 degree. Okay, so you are going to get your answer is 0.0809 meter Newton. Okay, so that's how you do this question. Okay, but the things that I need to highlight here, even though the answer should be counterclockwise, okay, The counterclockwise is going to be the answer if you see in this direction. Okay, so example, if I using that one, okay, so I'm going to get my diagram. This one, the first going to me away from me, okay, this one going to me towards. Okay, so because it's lengthened 30 degree, so it's going to be like this and like this. Okay, and the magnetic field there is going to be into the page. Therefore this is number one, this is number two. The directions of the magnetic field, the magnetic force going to be away from me into the page. So the force going to be here. Okay, and this one going to be here. Okay, so that's the reason why you are going to get this one is the anti-clockwise. Okay, but example, if the question didn't state in which direction that you need to see, whether this one or this one, okay, so you can give either one, but please make sure that you draw the place that you observe. Okay, whether this one or this one. Okay, so this for this one, because the question didn't state any directions, whether you observe in this direction or in this direction, so the answer going to be acceptable for clockwise or anti-clockwise, depends which way that you are going to observe. Okay, so but please make sure that you draw something like this. Okay, the place that you observe, to make sure that your answer is acceptable. Okay, so I think that's all for now. Okay, so if you have any questions, feel free to ask. Okay, so I'm going to see you at the next chapter. Okay, so thank you very much. Assalamualaikum and goodbye.